Hello students, and welcome to another video. I'm your teacher, Mr. Flynn, and today we're going to be talking about atoms. In the previous video we talked about how atoms make up matter, right? Everything that we touch and feel and hold in our physical world, okay? Now if we want to go a level deeper, now what makes up atoms, okay? And what makes up atoms are what we call subatomic particles. So there's a word here, subatomic, okay? Sub meaning below or under, and atomic referring to atoms. So it's like below atoms. So what are the parts of the atom? And there are three major parts to atoms. We have protons, neutrons, and electrons. And I want you to pause the video and I want you to write out these definitions for each of them. Okay, so pause the video, write them out. Okay, all right, let's keep going. And the electron, okay, I'll just say that. There's these three parts, and I'll come back to the nucleus in a moment. Okay, now if I come down here, all right, we've got a diamond, which is made up of pure carbon atoms, all right? And when we look at an atom, it's made up of two parts. We have the nucleus and the electron cloud, okay? That's where that definition up here comes from, okay? The nucleus is found in the center of an atom, and it is composed of protons and neutrons, okay? And the protons are green in this picture, and the neutrons are blue-purple colored, okay? And the electrons, we cannot see them because they are so small and they are moving very fast around the nucleus in what we call the electron cloud. Okay? Now, I want you to know all of this information for each of these subatomic particles. So a proton, its symbol is P positive, 1 plus, and its mass is about 1 AMU. I want you to write this down. All right? This symbol, instead of writing protons, I'm just going to write P positive. Instead of writing neutrons, I'll write N0, okay? And its charge is 1 plus, okay? And we'll talk more about this throughout the whole year, about what these charges carry and how important they are to the characteristics of atoms, okay? And its mass is 1 AMU. Now, AMU, we're going to spend some time later talking more about it, but the main concept is atoms are so small that we just can't measure them in grams. Okay, if we measure them in grams, we'd have a very long, complicated number. So what scientists have done is says, well, the mass of a proton and a neutron is about 1 AMU, atomic mass unit. Okay, the mass, right? Grams is measured in mass, right? We're using an atomic mass unit. Okay, it's now, instead of writing grams, we're just going to write AMU. Okay, but we are still referring to mass. Okay, so I want you to not confuse those, but just realize that they're too small to measure on a scale, so we came up with a new unit for the mass of an atom, or for subatomic particles in an atom, okay? Now, if we look at electrons, okay, the charge is negative, so we write E negative. If you notice that P positive because the charge is positive, all right? And the charge of a neutron is 0 because it's neutral, neutron, neutron, okay? And the mass of a neutron is 0.0005 AMU. So in other words, it's about 2,000 times smaller than a proton and a neutron, because they weigh about the same. All right, we'll actually talk about why they weigh the same in the nuclear unit toward the end of the year. But they both weigh about the same. And a mass unit for a electron is 2,000 times smaller than either of these. And it's very small. And I'll talk about, it's still significant to the a atom's characteristic set of properties, all right? An electron is very important, but it's very small, all right? So when we're talking about mass and those other things, we will actually not count it because it's so small. But you can't forget about them. They are very important when it comes to talking about the atom, okay? So just to summarize, we have protons, neutrons, and electrons, right? We have protons are positively charged, electrons are negatively charged, and neutrons have no charge. Right? The nucleus consists of protons and neutrons, and the electron cloud has electrons in it. Okay? That's the basic idea of how we're going to imagine what the atom looks like. Okay? And this is immensely small. All right? The size of this is very small compared to what, compared to something that we could shrink down in our life. It's really, how would I say it? Actually, I'll just use this example I have in the book. Okay? Atoms are extremely small. A single row of 100 million copper atoms would produce a line of only 1 centimeter long. All right, to give you a perspective of what a centimeter looks like. All right, this is a centimeter. you can fit 100 million copper atoms in a row in this small square in the centimeter. Now imagine if you wanted to produce a square of it, like a 1 centimeter by 1 centimeter, and then you wanted to make a cube of it. All right, we're talking massive numbers of copper atoms within a small given space. Okay, so they are extremely small. All right, let's go on to types of atoms. Okay, this brings us to more of the periodic table. All right, and you have one with you. It's in your green sheet. Looks like this. It's kind of reflective. Okay, and we have one in our classroom that we can look up at. Okay, now the atomic number. Okay, let's read this out. I want you to define this. So it's the number of protons in the nucleus of an atom. All right, so when we're talking about its identity, what makes oxygen oxygen is the atomic number. And if we look here at the top right corner of our periodic table, we see an 8. That 8 refers to oxygen has 8 protons. Neon has 10 protons. Chlorine has 17. Argon has 18. Okay? That top number is the atomic number, and it refers to how many protons there are in that atom. That's what gives each of these a different set of characteristics, because each of them have different numbers of protons. All right, so if we come down here, there's an easy example. We have helium and silver. Its atomic number for helium is 2. If you look at helium, it's kind of in the light. We have 2 right there. That's referring to the atomic number, and that atomic number actually represents how many protons there are. Now, if it's neutral, okay, we have 2 electrons. Now, if you remember the charges of protons are positive and electrons are negative. And when we have an equal number of positive and negative charges, they balance each other out and they cancel, and they don't carry a charge. So the positives and negatives cancel each other. So if you want something that's neutrally charged, it's going to have an equal number of protons and electrons. Okay. Now silver, on the other hand, we have 47 protons, and it's represented by the atomic number, and the number of electrons is 47 because it's neutral in this example. Okay. All right, here's a practice problem for you to pause the video and just mentally work on. Okay, if I were to give you a neutral fluorine and a neutral iodine, okay, what would be its number of protons and electrons for each of these? So if you want to pause the video, you can. All right, and I'll give you the answer. Okay, you'd have 9 protons and 9 electrons. Okay, it's the same as the atomic number. The atomic number represents the number of protons, not electrons. But if you want something to be neutral, the charges need to balance each other out. We need 9 positive things and 9 negative things. Okay? If we have a different number of electrons, that means our atom will have a charge, and we call that an ion. And we'll spend a great deal of time talking about ions in chapter 3. All right, when we talk about chemical bonding. Okay? All right, let's flip the page. I want you to define this word, the periodic table. Okay? There are 118 elements, all with different atomic numbers. They are organized into a table called the periodic table. A periodic table is an arrangement of elements in which the elements are separated into groups based on a set of repeating properties. All right? There is a reason why when you count across the table, it stops, and then you drop down to the next row. You go across, it drops down to the next row. Elements within the same column, okay, or group, have characteristics that are the same. And there's these repeating properties throughout the table. We will spend a whole chapter talking about this in chapter 2. All right, so it's okay if you don't quite understand how this table is laid out and why there's different colors. We will spend a whole chapter talking about it. But just keep in mind, when you look at the table, there is a reason why it's located where it is located. All right, and if you notice here, what is this top number at the top of all of these letters, these chemical symbols? It is the atomic number. And the atomic number represents how many protons are in that atom. Okay? All right. Now, let's get on to the mass number. Okay? So the mass number is the total number of protons and neutrons in an atom. Okay? Now, let's go back to our example of our periodic table. We were looking at oxygen, fluorine, neon a moment ago. Okay? This bottom number is the mass number. All right, you'll notice that all of my numbers are rounded to the hundredths place, while on my big periodic table in my class, it goes to like the 10,000ths place. All right, and in our laboratory experiments, we really only have numbers that are significant all the way to the hundredths place. Okay, so I don't really expect you to go further than this. So use this table whenever you're working on tests and such. And these numbers here, all right, refer to the number of protons and neutrons. Now let's make a connection here. Oxygen has 8 protons, and if it has 8 neutrons, it would be 16. Because you remember, protons and neutrons weigh the same. They have the same amount, 1 AMU. And if there's 8 of each of them, we have 16. Do you see how that works? This is doubled because we have 8 neutrons, 8 protons. All right, and we'll get to or later on why these numbers may vary. Like, why is this one 19? Because 9 plus 9 is 18. Why is this 19? Okay, it's not a hard, fast rule that there will be the same number of neutrons and protons within an atom. Okay, you will see that trend as you work your way down. You'll find that these elements get heavier and heavier because there's more neutrons in them. Okay, so for right now, all you need to know is this is the atomic number and this is the mass number. And the mass number is made up of the number of protons and neutrons. Okay, all right, so if we look at neon here, for example, all right, we have the atomic number is 10, so that means we have 10 protons, and its mass number is 22. So how many neutrons do we have? So 22 minus 10 would be 12. We would have 12 neutrons for every 10 protons for this neon atom. All right. Now, it's important to consider, what about the electrons that are floating around in this electron cloud? Remember how I was saying that they are too small to be considered significant? They are. They're 2,000 times smaller. Now, I want you to imagine that you have $2,000 and you lose $1. Are you stressed out of your mind that that $1 was not counted? Probably not. You're like, I still have $1,999 to spend. All right? You're not going to waste your time all over the city looking for that dollar. Right? So when we're thinking about atoms, we're only talking about the ones that are in the nucleus. They're the ones that are going to carry the most weight. All right? All right, so let's come down here. I want you to fill out this table, and I want you to make predictions on what it is that these are. All right? Okay? And I will go through it with you. How about that? I will do it with you. Okay? All right, so I'm going to pause the video. I want to fill this in, and then I will give you the answers for this. All right? So pause the video, and then I'll have you fill this out, and then I'll give the answers. Okay? All right, so you should have filled the answers out. And we have sodium, sulfur, silver, and gold. Okay, now if we look at sodium, the small number is going to be which number, the atomic or the mass? Probably going to be the atomic number, okay? Because the mass number is protons and neutrons, while the atomic number is just protons. So the atomic number for sodium would be 11, and its mass number would be 23, okay? And the number of protons there are is 11. Okay, the number of electrons there are, if it's neutral, would also be 11 because we have 11 positive things, we have 11 negative things. They cancel each other out. Okay, and the number of neutrons is subtracting the big number from the little number. Okay, the mass from the atomic numbers. Now 23 minus 11, that's going to be 12. So we're going to have 12 neutrons here. All right, and then we have sulfur, which is 32. That is our mass number. 16 is our atomic number. Okay, our number of protons would be 16. Our number of electrons would be 16. And the number of neutrons would be 16. Okay? Now, if we're looking at this next one, all right, it gave you the atomic number because it wasn't found with our chemical symbol. So if it says silver 108, all right, 108 is referring to, or sorry, 108. 108 is referring to the atomic mass of that atom, and the atomic number is 47. So if we find that on our periodic table, 47 is right here. Can you see that? 47. And here we have an average of the masses, okay? But this is the weight of just the one atom, okay? Because atoms come in different varieties, and we'll talk about that in the next section, okay? So when we look at the mass number for silver, it would be 108. Okay, well, its atomic number is 47. Okay, we know that silver is 47 because it's found on the periodic table there. So if we have 47 as our atomic number, that means we have 47 protons, and if it's electrically neutral, it will have 47 electrons. Now, 108 minus 47 gives me, you can barely see it, 61. That is how many neutrons there are. You will find that as atoms get bigger, they have more neutrons in them, right? This has 47 protons and 61 neutrons. And that's because as the atom gets bigger, it becomes more and more unstable. And the more unstable it becomes, it needs that buffer there to kind of help keep that nucleus together. And that's why neutrons are there. The purpose of neutrons and their neutral charge is to keep the atom from falling apart. It's to keep it from together, all right? And to stabilize the nucleus. All right, now let's do this last one. We have gold. So gold is 197. That's how many neutrons and protons there are, and our atomic number is 79. So if you look here, gold is right here in the middle. We have 79, all right? Just to let you know where that's at. So the mass number is 197, and we know gold, its chemical symbol is Au, all right? And we can determine its protons because there's a number of, its atomic number is 79. The number of electrons would be 79, but the number of neutrons, I need to calculate that. So let's subtract the two numbers. So we have 197, and we subtract that from 79, and that's 118. Can you see that there? 118 neutrons. Now the numbers are even getting more apart. There's even more neutrons than there were in silver. So if we look here, as we work our way down, and as we gain more protons, okay, our atom is getting bigger, we need more neutrons to stabilize the atom. Okay? All right, let's keep going. Isotopes. All right. All right, so I want you to write this word down. So isotopes are atoms that have the same number of protons but different number of neutrons. Okay? Now you can think of it like dogs. Okay? How many of you own a dog? All right? I have a dog. I have an Australian Shepherd. All right? And my neighbors have a Great Dane. But they're two different dogs, right? They're different sizes, but are they both dogs? At the end of the day, we both call them dogs. They just are different varieties of dogs. Okay? And the same goes with atoms. All right? Atoms can have different numbers of neutrons. So for example, we have oxygen 16, oxygen 17, and oxygen 18. All right? There's 3 different varieties of oxygen. It doesn't just exist as 16 and 8, right? It can actually gain neutrons and become a little bit bigger, a little bit heavier. All right? Now, what determines what an oxygen is its atomic number, the number of protons. All right? So oxygen always has 8 protons, but it does not say anything about having different numbers of neutrons. It's still the same atom, it just has more of those neutral parts to it. Okay? And if it's neutrally charged, then you'll have 8 electrons in each of these. So the only thing changing is the number of neutrons as you work your way across. Because if you subtract 18 from 8, you get 10. All right? Now, these atoms can come in different varieties, but in nature tends to side with certain types more than others. For example, oxygen 16 is the dominant one that we find the most of. Oxygen 17 and 18 are much rarer. We don't see them in nature as often. Okay? We mostly see oxygen 16. So there is bias in nature to what we actually observe in nature. Okay? We could create these in the labs, we can make scenarios where they exist, but if we were to collect a sample of them, most of them would probably be oxygen 16. Okay? And I'll actually tell you why I know that based on the periodic table and some calculations that we do in the class. Okay? Now, let's talk about atomic mass, and I want to draw some important characteristics here. I really like this example, and it talks about a piano and the atom. Okay, so if you think about the overall weight of a piano, it's very heavy. You see the cartoon videos where it falls from a skyscraper because they're trying to lift it on a roof, and it goes kaboom down the ground, all right, and it's very heavy. But let's think about the individual keys of a piano. If you took one key and you removed it from the piano, would it change the weight of the piano? Yeah, it will, but a very small amount. But would it really make a difference to the grand scheme of the weight of the piano? It won't. But here's the difference. If you're playing a piano, you're playing the piano, and you remove just one key, yeah, your whole song's going to be messed up because you're going to be missing that note. That note will be missing. The same goes for atoms. The electrons in the electron cloud, they may not consist of much of the weight of the atom itself, but they are very important. Okay, they are responsible for a lot of the characteristics of chemical reactions and bonding between atoms. All right, so you got to imagine electrons are extremely important, okay, but they don't contribute much to the weight of the atom. All right, so if you look down here, we actually have the masses written here for you. Okay, we have 1.67 times 10 to the negative 24 grams. You're working with a massive number. That is a hard number to work with when it's in grams. So scientists have just come up with a AMU. They create this new mass unit, because grams is a mass unit, but now we made a mass unit specifically for atoms. So protons and neutrons are both equal to 1, and the mass of electron is 0.0005, so it's about 2,000 times smaller. Because you can actually see that this is separated by 1,000, 2,000 or so of its mass. Okay? So just keep in mind, we don't measure in grams, we measure in atomic mass units. Okay? All right. This might be our last page I get to in this video, but we'll keep going. So earlier I was talking about how oxygen, when we go into nature, there's only going to be, the majority of the oxygen we find will probably be 16. There'll be 8 neutrons and 8 protons. These are other examples of elements like bromine, chlorine, and silicon that we can observe in nature and what is most common. So if we look at chlorine, all right, its dominant isotope would be chlorine 35. And chlorine 37 would be, it's in the, I'd say it's common, but not, it's not common. It's less common than what we'd find for chlorine 35. So for example, if I had 4 chlorine atoms, 3 of them would probably be 35. And then the other one would be just chlorine 37, right? And if I look at bromine, if I had just say 10 bromine atoms, the likelihood of 5 of them being 81 and 5 of them being 79 would be my case, because statistically, about 50% of the time you'll get one of each. So if you were pulling from a hat and you had 10 red marbles and 10 blue marbles representing these different isotopes, 50% of the time you're going to be pulling a 79, or the other 50% of the time you'll pull an 81. All right, so when we're looking at atoms, we got to look at it from a holistic view. Okay, you can't imagine that all the atoms that you're going to be working with are 79 or 81, because half the time they're going to be one of these varieties. And here with silicon 28 is the most dominant. Okay, when you basically are working with silicon, you're going to be working with silicon 28 way more often than 30 and 29. But does that mean that 29 and 30 don't exist? They still exist, and they're still part of the sample. So when we calculate it, we have to consider the 2 other isotopes there. All right, so if we look down here at our atomic mass numbers, we can actually make some pretty easy conclusions here. All right, so if you look here, the numbers that are in the whole number positions, not the decimal side, but like 79, 35, 28, all right, those are going to be your dominant atoms in your example. So if you see here, silicon 28, 28, chlorine 35, chlorine 35. And then we look here, we have bromine 79 is a little more common than 81, so our main number is 79. All right, and the numbers following that kind of drag your average based on where it's taking you. So for example, from chlorine 35 to 37, right, 37 is bigger than 35, so it's actually going to pull your average up a little bit. All right, so it's going to be 35.453, because when you work with chlorine in nature, 1 out of 4 of those atoms will be 37, chlorine 37. The other 3 of them will be chlorine 35. All right, and when you're working with silicon 28, you'll find that 29 and 30, the heavier isotopes, will kind of drag your average up a little bit. That's why this number drags out, because we're not working with individual atoms, we're working with a group of atoms, and they come in different varieties, and we have to consider their other isotope friends. All right, and if we look here, this number, bromine 79.94, kind of hits right between 79 and 81, because it's 50-50, but it kind of leans more towards 79. So if we look at this number, it makes sense that it's near 80, because that's what's between 79 and 81. All right, so there's two main factors that we need to consider when we're thinking about calculating an average mass, because this is an average between two isotopes and how often they occur in nature. Okay, so please, and also write down this definition down here. Okay, the average atomic mass, or the atomic mass for short, of an element is a weighted average of the masses of its isotopes. Okay, so if we come over here, all right, I want to show you this example. Okay, and this will be it. I think this is as far as I want to go. All right, so we have magnesium in nature, and it exists in three isotopes. We have magnesium 24, 25, and 26. All right, the most dominant form of magnesium would be magnesium 24, and then 25, and then 26. All right, and we have to consider, all right, how often they occur in nature and their weight. So the two things we really have to care about is their mass and their abundance. These are the two things we really care about. So the mass of magnesium 24 is 24. Okay, we've got a certain number of protons and neutrons equaling 24. Okay, so magnesium, if we look here, right here, magnesium is 12. Okay, so this is referring to having 12 protons and 12 neutrons. And it occurs 79% of the time. So how you'd calculate this is you would do 0.79, right? This is basic math. If you have 79%, when you type it in decimal form, it's 0.79. And we multiply that with our mass, which is 24, which is 18.96. But here, they round it up to 19. Okay? We have to do the same for magnesium 25. It's 10%, so it'd be 0.10 times 25, and it gives us 2.5. And then we have 26 times 0.11, and that gives us 2.9. Now, these are all parts. So what we're doing is we're saying this is the mass of one of the isotopes, and this is how often it occurs. Okay? And we're doing a part of it, and it equals 24.4.
Hi, students and teachers. Hey, we need everyone now to pull out their Chromebooks or their phones and look at an email from Mrs. Mitchell so you can vote for the homecoming royalty. So we need everybody to vote for homecoming royalty, and you just vote for one candidate. Thank you.
All right. Thanks, Sue. You're now embedded into my video. Okay. All right. So if you look at this number, let's make sense of 24.4. So 24 is our dominant, probably our dominant isotope. Because if we look here, 24 is the most common. And if you notice, magnesium 25 and 26 are a little bit bigger than 24, and that's what we have to consider because they do exist in a sample. So it's going to drag our average up a little bit to 24.4. Okay, so we're doing an average of the isotopes and what its mass is. Okay, you will do a lab in class with this with beans, and you will learn to calculate this with an example of like kind of what it would look like in a sample. If you do want to see examples, come talk to me in class. I have a jar of beans, and you can kind of get an idea of what I'm talking about. Because when we look at, actually, I'll just grab it for you, just to summarize this video. Okay, I've got this jar of beans. Can we see the beans in here? All right, we have white and brown beans in this container. Maybe I'll just leave it right here. Okay, and this represents a sample of the element Bg. Okay, it's beanium. That's what we're going to call it. It's beanium. All right, it's just an element that I made up, and each of these represents an atom of beanium. Okay, the white and the brown are two different varieties of beanium, and we call those isotopes. And if you look closely, the brown beans are a little bit bigger than the white beans. So the brown beans are going to actually make your average. It will actually, let's say this, because they are different masses, we have to consider them separately, right? And we have to also consider how many white beans there are versus brown beans. Okay, so those are the two factors in calculating a average of two different varieties of different quantities within a specific sample. And in nature, we know that magnesium will exist as 79% 24, 10% 25, and 11% of the time is 26. So we have to consider each of their masses and how often they occur to calculate an average. So when you look at your periodic table, all right, you can actually make assumptions about these numbers, right? So, for example, carbon is 12.01 and has 6 protons, and you can assume that most carbon atoms have 6 neutrons. But there are some out there, there's some other varieties out there that are heavier that kind of pull that average up a little bit, right? And if you're struggling with this concept, please come talk to me. But I'm trying to do a thorough examination of what these numbers mean, what they represent, and how do we relate them to making assumptions about this atom in general, okay? Thanks again for watching. If you have any questions, please come talk with me. Until next time.